That's all I want to hear.
Really recording on. Did we do the velocity transformations? That sound familiar? Okay. Really difficult between two classes this time. All right. So I have a rocket that's cruising along at some speed, we'll just say v, where v is relativistic. Inside the rocket, and that is the speed we'll flip Earth over here. And so the velocity of the rocket with respect to Earth is v. Positive v, like that's the positive direction. Somebody in the rocket is playing catch. Considering they have the technology to get a rocket at relativistic speeds, he's got something that he's throwing a ball forward at some speed. We'll just go with u. So that the velocity of the ball with respect to the rocket is u.
So we did do this.
We did do this?
Yes, there was a car and the ball being thrown forward at the car. Is that the same idea?
I don't think we finished it because I don't think it's where you wanted to go at that time.
Okay. Did we do, so what is the velocity of the ball with respect to Earth?
It's the velocity of the ball with respect to the rocket plus the velocity of the rocket with respect to the Earth.
So that would be, oh, I guess it, yeah, so given in terms of the letters that we have there.
That would be the, no, I don't.
What's the velocity of the ball with respect to the rocket?
U
Okay.
plus V.
All right, so all seems simple enough. So if V is, let's just say 0.8 times the speed of light and U is 0.7 times the speed of light, what would be the velocity of the ball with respect to Earth?
1.5 times the speed of light. 1.5.
There seems to be a problem with that.
Yes.
So obviously we can't solve it that way particularly well. It has to be another factor involved. And so we're talking about basically the addition of relativistic velocities. Because what we have right here is Galilean relativity. And recognize the time is different between the two. We generally think about speed as distance over time. And not only is distance different, but speed is different here. And so whenever you're given a summation of velocities, if you can set it up like the Galilean setup, like this is, you pretty much, that's the way I actually start those problems. There's an additional factor here. Whatever sign that is, it's the same sign here. And then it's my two velocities over c squared. And no, I did not derive it. Sorry for those who were disappointed. But if you could ever do it, set it up like a 151 problem, then the denominator is just going to be, again, the same sign, and then the two velocities over c squared. And so this becomes 1.5c in the numerator, and the denominator is 1 plus 0.7c times 0.8c over c squared, or 1.5c over 1.56c, no, over 1.56. And we get 0.9 something.
96.
C. And this actually prevents it, you'll never actually be able to exceed the speed of light because of this. Because the denominator will always be bigger than basically the numerator divided by the speed of light. Oops. do a quick turn around there. So the rocket is still moving off to the right. Since he's playing ball here, there's going to be someone over on the other side who's then going to throw it back at him at a speed of, same speed as before, just in the opposite direction. So let's set it up like a Galilean setup. We still have the same basic formula right here. The velocity of the ball with respect to the rocket.
Negative U.
Velocity of the rocket with respect to Earth. Over, depends on how you want to look at it. You can do it as 1 plus negative U times V over C squared. Or think of it in terms of V minus U over 1 minus UV over C squared. Either way you want to look at it to get to the same place. Let's figure out what this is with a marker hopefully darker than what I've been doing. So V is 0.8 minus 0.7 C divided by 1 minus 0.56. So 0.1 C divided by 0.44.
.23 C. Wait.
0.16 over 0.44.
Yeah, I did it right.
0.16 over 0.44?
0.16?
That's C.
1C.
Oh, yeah, that's. Just because I didn't
Yeah.
feel like bringing in the actual value. And typically, and this is one of the reasons why beta is used a lot, is the fact that, you know, whatever the speed of light is, you're still working all relative to the speeds, relative to the speed of light. And then as sort of a spoiler, we'll go for it anyway. And then one other issue that popped up early on is, are there any conservation laws? Do they still hold? Is conservation energy still a thing? Conservation of momentum? And so they came up with questions about this before I talk about conservation of momentum specifically.
Someone confirm that answer.
Yeah.
No need to confirm.
So if I have some mass here, M, let's just start out with, I have two objects. I have, we'll call this A and B. I take the masses and I sit them on top of a balance, I measure their masses, that all seems good. So that at rest, the mass of A equals the mass of B, which is equal to, I'm just gonna label it M sub 0. And now I'm gonna take that mass, I'm gonna take one of the masses, and I'm gonna sling it really fast. So it's kind of at some speed V at my other one, so we'll call this A, shooting really fast at object B, which is at rest. They're gonna collide in a perfectly inelastic collision, which means
I don't even remember if that was this semester or last semester.
It was last
Oh
semester.
my gosh. Inelastic. They.
perfectly inelastic.
Okay, elastic is they bounce.
Okay.
Inelastic is they don't bounce. Perfectly inelastic, isn't that what you called? They just stick together. They
They
stick
stick
together
together.
and then they stay together.
Yeah. So before and after, they basically are one thing, and they're shooting off at some final speed of u.
To clarify, should we review the collisions?
No.
Okay.
You I assume you just already knew them
Of course.
perfectly.
Perfect.
So if I did my momentum equation, so another reminder here, what's formula for momentum? P equals, I was hoping that would help, apparently not. If it helps you, we talked about impulse just before that. When someone suddenly buys you flowers. Oh, it's been so long.
Early semester, I was like really ready to pull stuff up, and right now I'm like, is it even Friday? Like I'm just confused.
I have no idea. All right, so
MV.
P equals mv. So I have the mass of A times V plus the mass of B times 0 is equal to the mass of A and B times U. Now, one thing, notice that I did not put m sub 0 down here, so just sort of keep that in mind. Now let's take a look at it from a different point of view. I'm debating at what point to do the hand wave. So I'm going to call this my S frame. And then in an S prime frame, so basically I want to get into the zero momentum frame. So that's what I'm going to be picking here. So after the collision, they're going to be traveling at this speed right here. And if I want my zero momentum frame, I basically have to move along at that speed. So if I'm moving along at that speed before, so my S prime frame, moving along at some speed U. What's going to happen is that A is going to be heading towards B. They'll be heading towards each other. And afterwards, they're just going to basically be stopped. Now, this is my prime frame here, and so the speed of A and the speed of B, well, they're not necessarily the same as U. Because if I'm trying to figure out how fast this is relative to what we have over there, or actually we can do one or the other, I'd have let's see, U prime is equal to so U prime plus, oh, okay. Just like we had just done, this is the rocket, this is the ball being thrown, Earth is the F frame over there. And so the speed, the velocity of A with respect to S prime plus the velocity of S prime with respect to S would be the velocity of ball A with respect to S. Again, those are the same right there. And ultimately trying to find the velocity of ball A with respect to S. Well, the velocity of A with respect to S is just this right there, V. Velocity A with respect to S prime is that right there, U prime. And the velocity of S with respect to S prime is U. But we're talking relativistic speeds. And so that's plus 1 over U prime U over C squared. So we suddenly have this, the velocity is not shifting. Like when we were doing these problems in 151, the velocities work very nicely. All you do is just add or subtract when we shifted from one reference frame to another. But now we have this extra factor here, which messes with that whole momentum thing. Because this was our momentum equation for here, and then in our S prime frame, we have the mass of A times U prime minus the mass of B times U prime is equal to 0. What I'm heading towards here, and so here's the massive hand wave, is that since the velocities don't translate nicely, the masses don't either. In other words, the mass of A here is not the same as the mass of A here, which is not the same as the mass of A here. Because the funky stuff that's going on with the velocities, something else has to be funky in order to get it to balance again. And so it turns out that mass is dependent upon speed. And as you might guess, the factor that you would throw comes into the problem now is a gamma. And so mass is equal to gamma times what's known as the rest mass. So when you get, and this becomes critical so that if I want to figure out what's in subatomic particles, I guess the Large Hadron Collider at CERN just got back up again after a 3-year downtime of upgrading. If classical mechanics were the valid thing, I could take my mass here and I could take a proton, I could shove it, ram it into another proton, they collide, and well, I have a little bit of mass to start with, and so therefore I just have a little bit of mass afterwards. I'm not going to see much. But at relativistic speeds, the faster I get that proton that I'm shooting, the faster I get it, the closer I get it to the speed of light, gamma keeps going up. In other words, it's like taking a really, really massive particle, even though it's just a proton. Take a really massive particle and I slam it into another particle, and I got a lot more energy there. A lot more stuff can come out of it. So a proton could be exploded, or whatever you call it, crash into something else and come out with a whole slew of other particles. Like one proton with enough speed can basically produce several protons, or actually, more realistically, thousands of them. Depends on how fast I get it going. Now, so this is known as the relativistic mass. Relativistic mass. Or not. As I'm looking at various literature on special relativity, there was one from University of Virginia, which was, I thought, really nice. The question is, what is relativistic, or so relativistic mass is a thing, and there's a couple paragraphs on it. And then the next section was, or not. Because there is a semantics issue going on here. So I have P is equal to mv, which by the relativistic mass standard over there means it's gamma times the rest mass times this speed. This would be the actual formula for momentum. Some physicists claim, they say mass is always the rest mass, that this is relativistic momentum. It's not the mass that's changing, it's the momentum that's changing. Just like with kinetic energy. Kinetic energy is gamma m v 1/2 gamma mv squared, or, actually that's not the right one I wanted. E equals mc squared, which would be, by the relativistic standards, would be gamma m sub naught c squared. So I'm treating this like it's relativistic mass, but some people look at that and go, it's not relativistic mass. The mass hasn't changed. It's relativistic energy. Now, just so if you're reading other literature, I read one thing yesterday that said, and some instructors are still misleading the next generation of students by calling it relativistic mass. Yeah, I have not seen any situation where the distinction between relativistic momentum, where mass is always the rest mass, or relativistic mass, and you're just plugging in that in for mass here. I've never seen a place where it really mattered.
So you're saying if we run into you on the street in like 5 years and you ask us what the formula for kinetic energy is and we reply 1/2 gamma m sub naught v squared, we would also be correct? Because you've made it clear we must know 1/2 mv squared.
Yeah, actually, okay, so
Please don't, you know what, I was looking for a laugh, that's all.
you got it, but you're gonna get more. I think that was a sign, that was, oh, joy?
Yes, that was a joy squeak.
All right, so when we're talking about non-accelerating frames, we're talking about things that are just moving at some constant speed. So there's no additional force involved on these objects, so we're not worrying about potential energy, which is associated with the force. So that energy, the E equals mc squared, is actually the rest mass plus the kinetic energy, which is why I erased it over there after I've written it up. So properly, kinetic energy is gamma mc squared minus m naught c squared, if you want to go that route.
So V has disappeared entirely.
Well, it's built into there,
Weird, okay.
so. I was trying to think of my dissertation. I don't remember how I had it. I think it basically did p squared over 2 MLI. Anyway, I'm good with 1/2 mv squared. But if you want to dazzle me with the fact that you remember this, even though you couldn't remember the formula for momentum.
Right.
All right, I think I've done that. There was a massive hand waving in there. I'm sorry I deprived you of some of the absolutely fabulous derivations.
To clarify, the takeaway from this portion of the lecture was which piece?
The fact that mass changes with speed is the big one,
Okay.
and the fact that relativistic velocities are a thing, that they don't add the same way that they did in 151.
Okay. I was concerned particularly about this S prime frame situation and if we would need to be able to reproduce that.
Conceptually, understand that it's just a different point of view.
Okay.
You said that the velocities don't add the same as they did in 151?
Correct.
The